Good afternoon, everybody. Let me start with a question. Who of you did follow our SDN presentation at the last PLNOG meeting? One. Okay. So I can ask you afterwards which one was better. No, I'm asking because what we did last time was going a little bit more deep into the theory of SDN. And today I would like to do a short review about what is SDN, what is it about, what do we need it for, why are customers interested in technologies like SDN. And then I would like to go a little bit into the details about how the technical implementation in a switch may differ from vendor to vendor to vendor, and what the development in SDN was over the last, I think it was about 6 months now, from the last meeting to today. So there has some evolution taken place, and I would like to shed some light on it and compare the status we have today to the status we had about 6 months ago. First of all, what are the drivers behind SDN? And there's a lot of needs from customer side for, let's say, automation in the network. So what we see is we have a big diversity of applications, of clients, of devices, users moving between devices but using the same application. That's the main driver for things like cloud computing. I thought it was quite interesting. About just 2 or 3 weeks ago, I read an article where they did a review and some interviews with German customers. And what came out is that at more than 30% of the companies today, there was cloud services already in place, although the IT department didn't have a clue of it. Because there was the need, but the IT department was not able to offer their customers, their employees, a cloud service. What they did is they used Dropbox, Boxnet, iCloud, SkyDrive, and all those available. So the company data slowly moved to a public cloud. The IT department didn't have a clue of it, and the security guys, they got completely crazy and said that can't be true. So there is a need from customer side, a need from user side to have something like cloud services, virtualization, and stuff like that in place. And if we as an IT department do not offer this to our customers, to our employees, they're going to find a way to get it from somewhere outside. So the question now is how can we, or what does it mean for technology? And let me find an analogy we have been seeing in the computer technology. So in the early 80s maybe, if you wanted to have a computer, you got something like this. Yeah, a mainframe, the IBM mainframe. That was the computer of the 80s. The issue with it was that it was a specialized hardware with specialized operating system and specialized applications on it. It was completely closed and proprietary, which means it was expensive. And that was the way a computer was built in the early 80s. And then we got the PC. And the difference between a PC and a mainframe is that it is open. It is an open architecture. Today, if you want to have a computer, you go into a shop, you buy the hardware, you buy the processor, the memory, the hard drive, and stuff like that, and then it's your decision which operating system is going to run on your PC. This can be done because there's an open and standardized interface between the operating system and the hardware. And on top of the operating system, there's the application. So you can even run different applications on different operating systems because there's a virtualization layer, a slicing layer in between. There's an open interface, and then it's your decision which kind of hardware I'm going to use, which kind of operating system I want to use, and what is the application on top of it. And when we look at the networking market, especially at the switching market today, we are pretty much the same status we had with the IBM mainframe. We have specialized hardware, we have specialized operating systems, and we have specialized application. So as of today, you cannot run Cisco IOS on an Extreme network switch, or you cannot run our Extreme Exos, our operating system, on a Cisco switch. You can run it on the specialized hardware which it was built for. And all those applications, those features, they come on top of this specialized operating system. And the idea of SDN now is to have a similar development that took place in the computing environment and put it into the network. So we are going to run merchant silicon, merchant switching chipsets you can buy from certain vendors. And then we have an open interface on top and an operating system, a network operating system that's running on this open and standardized interface. And those features we have today, like OSPF, BGP, MPLS, name them, they can run on top of the open network operating system and use the northbound interface, which is open and standardized as well. That's the idea behind SDN. And what does it mean for the technology? You need, in this term, you need to separate the control plane of a switch from the data plane. So each switch you find out in the market today has a control plane and a data plane. The data plane, when a packet enters the switch, looks at the packet, and then there are some tables that define the status of the data plane. And regarding to the status of those tables, to the status of the data plane, the decision is made to which port this packet is being forwarded, and if it has to be modified in a certain way. That's how all switches work. And on top of that, you have the control plane. The control plane defines the status of the data plane. The control plane feeds the forwarding table, the routing table. That's where the routing protocols work on. That's where a spanning tree or EAPS or any other redundancy protocol is running. And the control plane then defines the status of the data plane. And when you look at how a network does look at today, then this is how it is built. Okay, small one, yeah, just 5 switches, but in principle, that's how a network is built. And what you can see here is that each and every system is autonomous. It's just running for itself. It has his own control plane, his own data plane, and they talk to each other. But the decision is made by each and every system, which on the other hand means if you want to introduce a new service, a new application in a network like this, you have to touch each and every system. You have to configure them because they are autonomous. I need to configure the new service on each single switch in the network. And that's what is making the introduction and the delivery of, let's say, virtual machines in a data center so slow. Creating the virtual machine on an ESX server, for example, is quite easy, but the provisioning throughout the network needs manual configuration of sometimes hundreds or even thousands of devices. And this is why this may take not just a few minutes, but maybe up to 2 weeks before you can offer your customer, your user, the new service, the new virtual machine. And behind that, if we can automate this and if we can centralize this, then the delivery will be much faster. Another point is that in a network like this, there's no single instance, no central control. There's no single point where you can look at and immediately know about the status of your network. What we do today is that we go to each and every single system and read the tables. Yeah, we look at the routing tables, the forwarding tables, and due to our special networking knowledge, we can think about what is the status of our network. But there's no single place you can just look at and know this is the status of my network. So with SDN now, what we are doing is we are removing, if it works, we're going to remove, yeah. We are removing the operating system, the control plane from the switches, and put them in a single instance, which we call now the network operating system, or the controller. And between the hardware, the data plane still remains in the single switches, and the network operating system, we have an open and standardized interface. The controller has an interface to talk to the data plane. The control plane is centralized, and the control plane still defines the status of the data plane, but from a centralized manner. So what did we get now? We have one single central control instance, which controls the network. Okay, we had control planes before, but now we have one single point where we can have a look at and see what is the status of my network. And another point is, this is just a piece of software. So means introducing new features, introducing new applications, development cycles will be much faster than we had it before in the specialized hardware and the specialized network operating system. Developing software is much more flexible and faster than we can do it in hardware. This is one advantage this architecture gives to us. Another one is we can have a virtualization layer in between, and then we can even run different operating systems on one hardware platform. Just with another abstraction layer in between, the virtualization layer, we can have more than one operating system, specialized operating systems for special environments maybe, and then we have applications on top of it. And this also means that, you know, as it is just a piece of software, we can do what we can do with software. We can clone them, we can do a snapshot, we can say each and every day at, let's say, 12 o'clock at noon, we make a snapshot of our network. And if it's not working tomorrow, we can just easily go back to the status of the network, which was noon today. If you want to introduce a new application, if you want to introduce new services, you can easily test them by taking a clone of your controller, clone of the status of your complete network, and just before you introduce them, you know already whether this application is running in your network and working or if it is not. And you can easily test it. And at the end of the day, if this architecture is well defined, if the interfaces, the open interfaces are well defined and we can rely on them, as we do today in the PCs, we rely on the interfaces between the operating system and the hardware. If we reach a status like this in networking environments, then mistakes, issues just can happen in the controller. So it means all the troubleshooting can take place just in the controller. Makes it much more easy. We have one single place to look at and to troubleshoot and to find any issues. And that's the idea behind SDN. So let's have a look about how we do it. How does Extreme Networks do SDN? We have our hardware, of course, and we have our operating system, Extreme XOS, on top of it. And one advantage we have is that since we brought out Exos in 2003, that it is a modular operating system. So what we could do, very easy, was to add the open interface as a module to our existing operating system. And you're going to find these modules here. There's two modules. One is the OpenStack module and one is the OpenFlow module. And on top of that, we can have a management or control platform for OpenFlow and for OpenStack. And then we have all those applications which are now implemented as features into our switches being running as an application on top of an OpenFlow controller, for example. So what is OpenFlow? OpenFlow is one interface, a standardized interface between an SDN controller and the SDN capable hardware. So it has been introduced by the Open Network Foundation, which was founded at Stanford University. And founding members were companies like Google, Microsoft, Yahoo, Facebook. You see that the big ones, because they have the highest need of something like network automation or software-defined network or open flow. And what you have in open flow is that you have switches. It can be an open flow only switch, or what most of the vendors do, they add open flow capabilities to their switches, so that's a kind of a hybrid model, an open flow capable switch. Then you have the controller, and then you have flows. And when we look at the flows, what a flow could be is, it's quite easy, you know, there's a match condition, there's a match action, and there's some counters for statistics in those flow entries. So we are going away from legacy switching table entries and put it into flow entries in each and every switch. The match condition can be something in between layer 1 and layer 4. So just, you know, you define the match condition, a packet has to match. You can make it based on the physical port, the layer 2 address, the VLANs, the priority, IP address, TCP UDP port. That's what OpenFlow offers. And then on top of that, you have the action. If a packet matches the match condition of a flow, then do this. Like forward it to this port, or drop it, or copy it to several ports. That's what's happening in the match condition. And that's also where it is defined if you have to modify the packet, change the priority, modify the MAC address in case of it has to be routed between different VLAN boundaries, between subnets. That's all happening in the match conditions. And behind that you have some counters, so that the controller or a management platform or statistics platform can take out the counters and have some statistics gathered based on each and every flow. So, short example how OpenFlow works. We have two clients here, client A, client B. Client A wants to talk to client B, and on top of that we have the controller. The controller via LLDP gets information from the switches about the link status. So the controller knows the topology. Then client A wants to talk to client B. So what does it do? It sends out an ARP request, like it is done in every legacy network as well. The difference is now that the ARP request is not flooded as a broadcast throughout the network, but it's sent to the controller. The controller takes the ARP request and sends it out to the other switches in the network. And then it reaches client B. Client B answers with an ARP reply. The ARP reply is also being sent to the controller. And then the controller knows where is A, where is B, and can modify the flows in the way between A and B. So it adds the flows here in the switches, and then it sends the ARP reply out to client A. And now the flow is there. Client A can start sending out packets, and the communication is done between A and B. That's how it works. By the way, this is a great idea. If we have, let's say, an architecture like this, and you have SDN capable switches and an SDN controller for each and every edge device, that's the point where all your network access control, your host integrity checking, all endpoint security, it's no longer needed. Because if there is no flow, the packet is not going through. The controller says this client is allowed to this client. If this client is not added into the policy environment of the controller, it just doesn't add a flow, cannot enter the network, doesn't reach anything, you do not need any endpoint security anymore. That's another big advantage of what happens with SDN. So, now let's talk about how is it done or what happened over the last 6 months, and what is also the difference between single vendors when it comes to the implementation, because that's the point where we have big differences between the vendors. As I said, the interface is well defined. The commands the controller sends are standardized. What is not standardized is how the commands and the flows are implemented in the hardware. The controller doesn't care. The controller just says, this is the flow you have to add. How you do that, if you do that in an FTB entry or in a layer 3 hash table or in an access control list, I don't care. Maybe you can just do it in software. It's not very fast, it lacks performance, but it is allowed to do it just plain in software. So this is something you have to keep in mind when you are interested in an SDN solution. Look at how it is implemented in the hardware you're gonna plan to use. That's the biggest thing you have to keep in mind when you test an SDN solution. So what we do is we have different functionalities, and based on the kind of flow, we add the flow entry in different parts of the switches. I'm going to show you a little bit more about this. Let's take an example. Let's talk about link aggregation. And here's where, you know, theory and real life maybe do not work together quite well. Because there's two ways you could do link aggregation in an open flow network. One way is you could leave the decision and all the hashing to the controller. Hashing means, you know, link aggregation, we have, let's say in this case, 4 physical links. We form one logical link about it, but one packet is only crossing one physical link. Who is going to make the decision which physical line in this logical link will be used by a single packet? So where do we add the flow? There's two ways. One could be the controller makes the decision. The controller makes the hashing, which is not very scalable, which has the disadvantage that the controller has to do much more flow entries, and in case of a physical link that breaks, the controller has to modify the hashing very, very fast. That doesn't scale. So what we decided is that we do the hashing in the switch. The switch decides on a logical link which physical link a packet is going to use, just as it does today. This has one issue. We are no longer following the real SDN theory then, because in SDN theory it says the switch itself is stupid. The switch itself has no abstract or no complicated functionality in there. If we do link aggregation, hashing, based on the capabilities of the switch, we either have to configure it again, or we have to use things like LACP to have it automatically configured. Or we have to use the controller has to be capable of finding out that there's more than one physical link and configure the switch to a link aggregation group. And the same with quality of service. What the controller just says is, this is the priority of a flow. It can make a flow entry and say this is an important flow, like priority 7 or priority 5 or priority 3. The controller does not take care about how it is implemented in the hardware. That's made by the vendor of the hardware again. So this is something you have to keep in mind when you look at SDN-capable switches. So what we do is we use different tables. There's different tables in a switch anyway. We have a layer 2 MAC table, we have a layer 3 LPM table, we have a layer 3 hash table, and we have access control lists. And depending on the complexity of a flow, we are moving the flow in one of these tables. When the controller is looking at the switch, for him it's like one table. He's just adding flows. That's why we call it a kind of unified forwarding table. Yeah? But the table itself is stored in different parts of the hardware depending on the complexity of the flows. That makes it much more scalable. We could do that just based on dynamic ACLs, which would limit the amount of flows we are able to add into our switches to a few 10,000s maybe. By using the layer 2 table and the layer 3 hash table, we can scale up to 1 million flows in a box as with the technology of today. So there's the layer 2 table, the layer 3 table, and the access control links. We are running a little bit out of time, so I'm going to skip this. Here's, you're going to get this presentation. Here you can see which of our gear is OpenFlow capable. Short view about the roadmap. We are right here, or between here and here right now. So in February, we've brought out the first implementation with OpenFlow 1.0 in Exos 15.3. And then we added some more capabilities in between, like forwarding database-based flows, VLAN modifications, so we can have more than one OpenFlow VLAN now. We have routing mechanisms in place. In 15.4, expected end of the year, we're going to put this all into one general availability or one major release, and then we expect to have the full OpenFlow 1.3 implementation in February of 2014. So just a few screenshots of different controllers we support. Right now we have partnerships with Big Switch, with Floodlight, which is the open source version of Big Switch, with NEC, and an upcoming partnership with VMware regarding the NSX. Here you're going to see a screenshot of a network set up of 8 switches running with the Big Switch controller, and on top of that we have a software that's called Hyperglance from Real Status, which is a visualization tool for SDN controllers. The nice thing is you just plug all those switches together, you add the IP address of the controller, and you're done. Setting up a network like this, fully meshed, takes you just minutes. And if you want to add a new switch, just plug it in. The controller finds it out, and there's no need for loop protection, traffic engineering, stuff like that. It's all relying in the controller. And with Hyperglance, you can visualize this. When it comes to Floodlight, there's the dashboard of Floodlight. Here's, this was a 6-switch network. Here's the switches. Then we have a topology view, which is, I think they can improve it a little bit. You cannot modify this. If you move switches around, it automatically redraws and stuff. So it's terrible, not really good looking. But there's also a Hyperglance version for Floodlight and for NEC as well. So here you see the different ports. Here's the flows that has been added. As I said, you're going to get this presentation and you can walk through it afterwards. So let me come to the conclusion when it comes to SDN. What is going to be the future of SDN? To be honest, I don't know. Is OpenFlow the protocol that's going to be the future of SDN? Maybe. On the other hand, there's another foundation called the Open Daylight Foundation, which are setting up their new controller, their own controller. So there's a lot of things going on in the networking market. But what is clearly sure is that the need from the customer side is there. And there will be something like SDN in the future. There will be automation in the future. Right now, we cannot really 100% predict which way will be gone. And I can just invite you, come over to our booth, and we can discuss about all the different possibilities that SDN is going to offer and what's going on in the market there. Let me just, when it comes, why do we as a switch vendor implement SDN? And I already talked about the implementation in the hardware, and I normally use an analogy when it comes, think of an SDN-capable car. You have a car that can talk OpenFlow. You have a car which has a high abstraction level, and you just give commands, drive left, drive right, accelerate, brake, yeah? And now you tell your car, go 250 kilometers an hour. And there's a virtualization layer which says, okay, 250 kilometers an hour means engine full power. And then there's the operating system which says, engine full power means fuel injection to maximum. So that works. But then, this is your hardware. Yeah? 4 cylinders, 1.2 liters, with amazing 34 horsepowers. They will do their best, but they will never go 250 kilometers an hour. So although the hardware understands your command, it is not capable of following it. What you need to go 250 kilometers an hour is a hardware like this. And the same for switching. It's nice when a switch is able to understand the commands from an open flow controller, but if you want to follow it, the implementation has to be there. You need powerful hardware, you need scalable hardware, and that's what we always were building, and that's what we are going to do in the future with SDN as well. Thank you very much.